believe it or not, we're coming upon our election, so I want to briefly mention that as well. Next slide, Dave. The slide you've seen often. This is where you find out information. The cool QR code will take you right to our club website, and there's a calendar readily available that is updated daily, really, depending upon the weather, whether or not events are going to run. So it's a really great resource to find out when and where and what's happening with the club. We also have a pretty active IO groups where there's tons of topics in the archives, but you can always post a question, and a number of very helpful members be happy to help you out. Of course, we've got our YouTube channel where most of these programs are available for you to watch or rewatch. Our Facebook page has a ton of really nice astrophotography, as does our Instagram page. One thing that I want to mention here that I probably don't stress enough is that when you're wondering what's happening with the club, and we always encourage you to attend the board meetings where we discuss all the business that's happening with the club, a great summary is always available in the newsletter, and we have quite a few newsletters archived on the SDAA website. So if you're wondering what's happening with a particular project or a group, please check out the newsletter and read the board minutes. One of the requirements of board members and also committee heads is to provide summaries of what's been going on with that particular project. And, I think you'd be surprised if you haven't checked out how comprehensive some of those reports can be month after month. So if you can't make it to the business meetings and you have a question about a particular project and what the status is, please take time to read those board meeting minutes, because there's a wealth of information available in those. Okay, let's move on to the good stuff. Next slide, Dave. Some cool space news. I don't know if you guys checked this out, but since our theme is of the future, last month, the Colorado-based Lunar Outpost, I never even knew these guys existed, unveiled its new Eagle Moon rover at the Space Foundation's 40th Annual Space Symposium. And I mean, this thing looks straight out of something from science fiction. It's got a sleek metallic finish and ice blue LED lighting per the description. And it has more than just futuristic looks. I always love reading this about design and future, and that is they actually have astronauts involved with the design and the feedback. So this particular rover is packed with features designed with the next generation of the Artemis program moon explorers in mind, and it's based again on the feedback from NASA astronauts at Johnson Space Center. And what they're doing is, having the astronauts in their full pressurized suits actually testing out this vehicle, and, given the feedback, they're making changes. So what we're looking at right now, just as an overview, is the forward seating area. Next slide, Dave, of the Eagle's Moon rover front seat. There's a huge, wide, accessible area. As you can imagine how bulky the, spacesuits are. There is, let me just quickly read the description here. In the configuration shown, the Eagle vehicle features 2 front seats for crew, each with its own redundant and mirrored controls, meaning either astronaut can control the rover, and the steering controls on each side consist of a single handle that controls 4 individual motors that drive each wheel. And this actually allows the vehicle to crab walk, which I think is really cool. I wish a lot of cars on the streets had that for parking situations, but these are just all these new features that they're adding in addition to the hand controllers. Next slide, Dave. Each seat in the Eagle rover has a multifunction display at eye level for each of the astronauts riding on board. These displays are fused with onboard cameras. They have eagle eye sensors that can see things astronauts' eyes can't, which will come in handy if the vehicle is ever sent to explore regions near the moon's south pole that contain permanently shadowed regions or deep craters where water or ice might be hiding. So the idea is to extend the crew's perception, and the display puts all that information right at their fingertips. One of the other really cool things about this is that it will actually be able to be operated autonomously or by controllers on Earth. So that will allow it to explore the lunar surface, even if astronauts aren't on the moon on board with it. So to summarize, Lunar Outpost hopes to have Eagle on the moon by the end of the decade to support NASA's planned Artemis 5 mission, but the rover is currently in the running alongside two others, which I didn't know about, designed by Intuitive Machines and Venturi Astrolab. The total potential value of this entire lunar terrain vehicle services contract is $4.6 billion. I say money well spent. So just a little bit of future of what these rovers now look like, completely different from what I remember from pictures. Next slide, please, Dave. All right. And talking about the future, I was at lunch with a good friend, Bill, of mine yesterday, fellow member of the club, and we were talking about our 3D printers. Now, I'm sort of new to this field. I got a printer about a year ago, and before I bought my printer, I was under the impression that, you still needed to know how to code and you still had to pay a lot of money for a 3D printer. I'm glad to report that the world has completely changed in 3D printing if you are not aware and have one yourself. You don't have to know anything about coding for the simpler ones, and they're actually quite reasonable to purchase, many of them being plug and play. So here's a picture of my 3D printer is a Bamboo, and this is Makerverse. If you haven't checked out Makerverse, if you're new to 3D printer or have been doing it for a long time, you can virtually find anything astronomy related to print. Again, you don't have to know a whole lot of coding even to make changes to the models that are available for printing. Next slide, Dave. This sort of launches me into my member survey question, and that is either in the chat box during this meeting or by way of sending me an email. Let me know if this is a topic that you guys would like to hear about, all the way from, I don't have a 3D printer, how can it help me with my astronomy hobby? Or if you are very experienced with 3D printers, would you like somebody to come on board that actually has a lot of experience with it and can point you in different directions for what you're looking for? Dave, can you go back to the former slide? There pictured is this contraption that I just happened to find and thought was awesome, the microscope, which when you read about the description is actually a go-to scope that you can 3D print, and then by incorporating a couple of Raspberry Pis, turn it into something that you'd normally buy. To the right is what you can find on eBay right now. I'm surprised to see how much the prices have jumped for people that are offering pieces and parts for various pieces of astronomy equipment. But I mean, if you end up getting a 3D printer, you can print a lot of this stuff yourself. The STL files that are required for the printer to run from are readily available. And with all kinds of free software right now available online, you can actually tweak those objects to customize what you need and or create something you completely have thought of on your own. So again, please let me know if this is a topic you guys are interested in. I would love to bring in, somebody who knows quite a bit about it. And I suspect too that there's probably a lot of our members that have spent many years working with 3D printers and could also be a great resource. So don't be shy. Let me know in the chat box what you think about having one of our program meetings on that topic. And also you can send me an email. My email is on the contacts page on the SDAA website, along with all the rest of the board members. All right, coming up to the end of the agenda here for my part. Next slide, Dave. Can you guys believe we are coming upon an election? There is a typo in this slide. My apologies. It should say coming in November of 2025. That is the election. We are trying to avoid last year's election where we were really rushing along with all the new things we had to incorporate after the big reveal. This time, we want to stress that we want you guys involved. It would be so awesome to see new faces, whether you've been with the club for a long time or you've newly joined and feel like you'd want to be in leadership with the club. We would welcome you. Love to see new faces. So here's what's on board for the positions starting in 2026. 4 director positions, which are 1-year terms. The vice president will be replaced. That's a 2-year term, and also the corresponding secretary, 2-year term. The reason it's not the whole board is we stagger them. Obviously, that makes sense. Next slide, Dave. We always get questions. Well, what are you guys looking for? Here are just some very, simple guidelines. Not that this is anything new, but you do have to be willing to commit time, especially given the way that our club has grown and our new responsibilities. It's dynamic, it's always changing. We need people who are going to be available to commit time, not just to board meetings monthly, but also to consider chairing some of the many committees that are forming, it seems, all the time about the things that club members are excited about and want to see. It'd be great if you volunteered with any club, not just San Diego, or you have experience again in leadership that could help push us forward. This is probably super important. Please be an independent critical thinker, not just an agreeer, somebody who's just going to check off the boxes. We want to hear good ideas. We want to be able to debate them, nice robust debates, and then collectively come together to a decision that's best for the club. I guess that's the last thing. Be willing to act in the best interest of the club. And I also want to add here too, if you ran for the board last year, please consider running again. We had such a great turnout and so many excited people. It's a shame that we couldn't just have a position for everybody on the board. But if you ran for the board last year, please, we'd love to see you again. So that's the election is coming in this November, but very soon we'll be asking people to submit their, forms of interest. We'll probably do what we did last year again, and that is have you write up a little biography about who you are, and in what ways you would love to participate in the leadership of the club. So the election is in November 25, but pretty quick here, we should be making efforts towards soliciting members to introduce themselves to the general membership and say that they're interested in running for the board. Okay, I think there's just one more slide, Dave, before I hand it off to our featured speaker tonight, Tom Field. The upcoming SDA programs in July, we've got the first place winner, the Greater San Diego Science and Engineering Fair. That's going to give a quick 10-minute summary of the project that won first prize. We've got Neil Farber with the topic of astrobiology. And then in August, something pretty special, we've got Richard Wolf Jacobson, who's going to talk about Pi Finder, which I think, at least some of our members are actually using. Okay, without further ado, I want to welcome, thank you so much, Tom. I guess you're a repeat speaker. What did you say, 11 years ago? You were actually here talking to us, and here you are again.
Yep.
The title is You Can Almost Touch the Stars. This is an intro to spectroscopy. Welcome.
Thanks so much, B. Thanks. Can you all hear me, Dave?
I can hear you, Tom.
Yeah, you can.
Okay,
You're good
thanks.
here. Yep. Good.
Thanks, B. So good evening, everybody. Thanks so much. And B and Dave and Marianne and all the others who made my attending tonight happen. This behind the scenes stuff that they all do to keep meetings like this populated with speakers is really sort of an unsung hero kind of thing. So I've got a ton of material to cover tonight. I'll tell you a little bit more about my background as we get into the presentation. If I go out of PowerPoint, because I do want to show some other things and forget to come back in, please remind me. So, when I look at these stars here, this iconic image here, sometimes I wonder, what about all these stars up in here? What don't they feel a little bit like looked over or something? The fact is, every star has a life story. And I was thinking earlier today that, again, I like to change up this talk a little bit. And there's three things that I'm going to talk about tonight. One is learning about the astronomy that we do. The second is actually doing it ourselves. And the third is giving back and educating others. And all three are things that I want to talk about tonight. This is a rather old-fashioned slide. and we are standing on the shoulders of giants. If I was in this image, I'd probably be on the back side of this building here, looking the wrong way. But there are an enormous number of people that we all have to thank for so many things. Robin Leadbeater is one of them that I thought I'd mention right here. But for me, the learning part, and we are learning machines. If you all have young cousins or kids or grandkids, you see they are sponges. And I think that sticks with us. We all have this desire to learn more. And my story is that I wanted to learn more and I was a little frustrated. First of all, it's like trying to drink from a fire hose these days, right? And secondly, you never know exactly what level to be at, and that commitment to learn eggs and ebbs and flows. And so I wasn't sure how to get started. And the theme tonight for me is going to be just how exciting and effective spectroscopy has been for me in learning a lot more in an unpressured, self-guided, motivated environment. Just a quick look here. I know some of you are familiar faces here. Dave is using my software, and so are some of the others here. Chandru Narayan is also a friend of mine. He teaches, and we'll talk a little bit more about that as we move on tonight. So we're going to look at some of our beloved constellations tonight, just starting at Orion here. We can see the three belt stars, and we can also see that each of them has its own unique spectrum. That's what we're going to dive into tonight. They say like 70 or 80% of the science that gets done, the astrophysics, our understanding of the stars, came out of spectroscopy. So even if you're not an active observer or imager, or this turns out just not to be for you, I think this talk will give you a good foundation on what it's all about. And so the next time you're reading a magazine that they mention spectroscopy, you'll have a little bit better idea of what it's about. This is a large star field in Perseus. And what do we have here? I mean, to be a devil's advocate, it's a boring star field, right? There's a bunch of dots. Most of us are looking at deep space objects. And this is just a bunch of dots. There are three stars here that we're going to take a little bit deeper a dive in as an introduction. This is a DSLR image of those stars, those three stars, and you can see to the right their spectra. Now, the reason I wanted to start out with a DSLR image is because that's one of my themes is you don't need big aperture, you don't need dark sky sights, you don't need all the high-end equipment that makes astro imaging expensive and produces fantastic images. So if we look at this first star here and its spectrum, just really qualitatively, we can see there's some gaps in the spectrum, some dimming spots, and that's primarily where we're going to be focusing our attention tonight. And without getting into the details, this is a type of star that characteristic set of lines indicates something about its history. Now, we'll do a little bit of science tonight just to get people to the same level where we can talk about things. Just a brief reminder that each element has its own fingerprint, and we'll come back to that later. But the fingerprint of this star tells us something about it. And on this scale down here, which is a temperature scale, this is a cool star. It's a type M star, so it's over at this end of this continuum. Quick story. About 15 years ago, my wife was driving. She had her Garmin. That dates the story. She was going to a strip mall somewhere outside of Seattle, and she did the shopping she had to do there. When she went to leave, she didn't turn her Garmin on. She got to the exit, and she literally, she told me, didn't know which way to turn. So maps are helpful, and so I found for myself, and so many people have found that cognitively, in terms of memory, in terms of learning, having a map is a big advantage. So some of you will recognize this as the lower axis on something we won't spend a lot of time on tonight, the HR diagram. If we add another axis here, which is star intensity, we have temperature here going lower there and intensity going higher there, then we get this beautiful image here with enormous amount of data. The sun is there, so the sun is a star down here, a G star. And there's Vega, or lots of beloved stars, Spica. So the star we're looking at is up here, that first star in the DSLR image. So this kind of map acts as, it's sort of in my mind like a pegboard, that as I observe stars and learn a little bit about them, I can put a pin in that part of the chart and learn more about that particular type of star. And that serves me much like a printed map would have served my wife when she was trying to figure out how to get home. So that's that star. Now, if we look at this star here, notice that it's got some bright spots, actually just one, maybe two bright spots instead of these dimming absorption features here. This is what's called a BE star. And a BE star, again, this is all stuff that I sort of knew from reading over the years. But once you capture the spectrum yourself, it's a whole different ballgame. It's more interesting. You're more interested in digging deeper, and you dig as deep as you want. So it's not like, oh my God, I've got to get over this tsunami to get to the other side and understand anything. You learn what you're curious about, and you have a starting place with the images you capture. So this is a circumstellar disk of hot gas that's glowing right there. That's what the E in the BE star stands for. So a BE star, oops, I've already done it. Let's get back over here. Usually I don't screw up until later in the presentation. Let's get through here. There it is. Usually, sorry for that. This star here has a lot of bright lines. So let's take a look at it. It is a really hot star. So it's a Wolf-Rayet star, and we'll look at what that means in a second. I may have gone past that slide in my hurry here. It's a really hot star and very bright. The star we were looking at a few minutes ago was a B star a moment ago, so it's somewhere up in here. So we're beginning to put those pegs in the pegboard for our understanding of how stars go through their life cycle. Most of the stars, for those of you who aren't familiar with this, are on this line right here. But understanding this is that map that I spoke of. Let me go back to see if I thought I had a Wolf-Rayet star here. Maybe it's on the next slide. There it is. There, it's a late stage star. It's blowing off diffuse gases. You can see down towards the core. These are byproducts of the star burning. And if you capture a spectrum like this, then you start going out and reading this kind of thing because it's interesting to you. And you can see these are very hot stars. So that's just a quick overview that I wanted to share with you and of the HR diagram and how we can do exciting work with it. And when I say we, I mean every one of you who's done any imaging. So the way we capture these spectra is with this 1.25" grating. It's called a star analyzer grating. It's a couple $100. I'm going to demonstrate it to you here. I have a gas tube. I'm going to turn it on, and I'm going to hold the grating up to my camera. See those spectra there, all those lines? Those are the lines for the gas in this gas tube. And whether it's a gas tube or a star, it's the same lines. And that's what's, yes.
We're not seeing if you're we're still seeing the video of the picture of the grating.
Okay. Oh, I forgot to stop sharing my screen. Let's do that. Thank you. That's the kind of interruption I wanted to have. So here is the gas tube. And it's a helium gas tube in this case. And here's the star analyzer. If you guys can't see that now, let me know. But you can see that this grating splits the light just like a prism. And screwing this on to your imaging camera allows you to capture spectra. Let me go back to sharing my screen. We'll go like that, and we're back. Now, how do you mount this star analyzer? Just really quick, because we have a lot to cover tonight. The takeaway from this slide is almost any camera. You can put it on the nose piece of a guided DSLR or a tracking DSLR. Put it on your FITS camera. It doesn't have to be a color camera. DSLR on your telescope. You can actually capture video, and I'll show you some of that tonight. Or you can put it on a filter wheel. So however you might be imaging or starting to image, you can do it with a star analyzer in almost every case. So just a tiny bit of history here, just again, to get us all to a fundamental understanding. I apologize for moving so quickly. Sir Isaac Newton is said to have used a prism to split light into its component colors from white light. And by the way, I don't purport to be an expert on, certainly not the history or the science. There are some of you here tonight who will be able to correct me as we go into the Q&A or by email directly. You can split a white light into a colored light. You can also split it into its colors by bouncing it off a finely lined surface or through a small diffraction grating. By the way, Can Gary, you're there. Can you see me as I'm talking, or
Yep,
am I not? Okay, great. I just
everything's
wanted to
good.
know.
Yeah.
Wonderful, thanks. So some of you may have encountered Bunsen burners in college. Bunsen invented the Bunsen burner to burn a sample, put it through a prism, and observe the results. And he was a real pyromaniac. He burned everything he could find. Interesting thing about Bunsen is he deliberately didn't patent it. He said, "This is for the good of humanity that I'm going to not patent this." Now, today he probably would have had an LLC and a patent, and who knows what would have happened. Kirchhoff we'll talk about in a minute, but again, this is just a really brief background. So these are those fingerprints. Each element has its own fingerprint when you're looking at its spectrum, split by a star analyzer or a prism or other device. Hydrogen is so common that we've actually named these lines, right? Hydrogen alpha, this is a hydrogen beta. What color should we call that? What about calling that robin egg blue? Well, because we're going to come back to that line and then finally another line. So one bit of lot of information on this screen. I just wanted to show that hydrogen has a different spectrum than helium. This is a poster that we put together some years ago. I've got some stories about Neil deGrasse Tyson in this poster, which I won't have time to tell during my talk. There's that robin egg blue hydrogen beta. So what do all of the astronomers who I've mentioned so far have in common? They're old white men. So there's tons of people who aren't that who have contributed to our fundamental understanding and state-of-the-art research in the field. I just wanted to go through some of those. Annie jumped Cannon and her computers more than 100 years ago. That's what these women were called, were prohibited from accessing the Harvard telescopes. So they studied photographic plates. They studied over 400,000 spectra, and they came up with, from that just deep saturation and immersion, they came up with a categorization scale that's really helpful. Priyamvada Nataraja is at Yale. She studies hyperactive black holes. Nancy Grace Roman, sorry for the rush, folks. It's even harder for me to give these talks when I'm talking to clubs that are overseas, because then I know I've got such a strong American accent, right? That I have to slow down a little bit. Nancy Grace Roman was the first astronomer at NASA. Imagine that in the 40s as a woman at NASA, the challenges she must have faced. Jedediah Eisler's at Dartmouth. She studies, I think it's hyperactive black holes, and Elisa Quintana studies cool type M stars that might have exoplanets. She actually looks for the exoplanets. Suppose a type M star, which is a red star, suppose it had life. This is a NASA idea, let's say, of what it might look like. There's more red light, so the plants end up, instead of being green, being red. It's sort of a cool representation. So I just wanted to spend a moment talking about these contributors to the field. Okay, enough of all this arm waving. What can we actually do, right? That's what we like to do. History, theory, equipment is important, but the actual doing. Here's what I'd like you to come away from really quickly today. It's a wonderful way, as I said, to gain a deeper understanding. It's easy to understand. You can easily do every spectrum I'm going to show you tonight, unless I call out otherwise, was done with a star analyzer, and often with a DSLR or a 4 or 6 or 8-inch telescope. You can do it from light polluted skies. You don't have to go out to a remote site or have a remote telescope. Excuse me. And I think that's it. There we go. Now, to be honest, I don't know why this slide is in here. I must have been sorting them today and somehow dropped this in again. So how do we do all this? Well, here's the star, and we put a star analyzer in the light path, and then we just take an image of the result. And we can see the star here and the resulting spectrum here. Now, even though many of the spectrum tonight are going to be in color, you don't have to use a color camera. As many of you know, a color camera isn't as sensitive and has some other problems. And by the way, I want to talk in a little bit. I wanted to show you some of the sizzle first, but I want to talk about how you can use these kinds of tools in star parties, in educational outreach. Boys Astro, I know Pat spoke last week. I'm going to talk a little bit about the work we're doing there, Chandru and I, the kinds of educational opportunities that are available. And I think this is one of the best, if not the best opportunity to actually do outreach in an educational setting in your town. You heard Pat say, a month ago, if you were in the meeting, how difficult it is to get into schools. Well, we've got thousands of schools using our products, not only astronomy products, but also some others I'll mention. And we're in front of chemistry teachers, physics teachers. There aren't that many astronomy teachers out there. So with the tools I'm going to show you, and I'm postponing that for a little bit, this is just a little foreshadowing, opportunities for you to really make a difference in students' lives. And I think you'll find that pretty exciting. Here's our first qualitative example. Each of these is a different spectrum captured at a different time. The cool type M stars are here. The hotter stars are up at the top. Those are the type B stars. We're not going to spend a lot of time on this. Torsten Hansen captured this on an 8-inch Newtonian with a video camera. That gives you an idea of how easy this stuff is to do. Why is it so easy? Well, first of all, the demands aren't that high. It's not like an image where we're, a visual image of some galaxy where we want the fine gradients and we're going to be stacking lots of images. We're just looking for gaps. Now, as you get into more quantitative, then dark skies certainly help. But there's so much we can do with the thousands, literally thousands of local stars that or bright stars that are, mag 3, 4, 5. So you don't have to be digging. You don't have to be struggling, for that. I'm going to say it. I've never thought of it this way. For that macho kind of, yeah, man, I'm looking at a, magnitude 17 star. Okay, fine. But with this, you actually get actionable and interesting data. So the two things we are going to look at here, one is I just want to point out these really wide bands, these forests of lines on these type M stars. Now I'm going to tell you everything I know about these lines. I'm not proud of it. I'd love to know more, but I've learned other things instead. And I say that just to point out that you learn as much as you care to, but with just a little knowledge, you get a lot of understanding. So these are from titanium oxide. So titanium oxide, all I know about it is it's a molecule that doesn't get burned up because these stars, these type M stars down here, have such a low temperature relatively to the hot stars. Now, the other thing I want to look at is this region right in here. What would you call that color? How about robin egg blue, right? That's our hydrogen beta line. That's hydrogen right there. One other quick thing here, and that is you notice it's darkest or widest there because this star is just the right temperature for that line to get created. And how do these lines get created? Really briefly, in 20 seconds, you'll remember from perhaps high school, the Bohr model has orbitals around the nucleus in the atom, and they're numbered. And when an electron jumps from nucleus or from orbital 2 to orbital 4, it absorbs energy at just this wavelength. And we're going to look at how you can bring that into a chemistry classroom if you want to do outreach of that sort. So that's how all these lines are created. And that's why chemistry people, chemistry educators are interested in this. Oh, I did it again. Let's come back here to, sorry about that, to this slide. There we go. Okay, so let's move on here just really briefly. Some of the spectra you're going to see here tonight have gaps. Some of the spectra have dark background with bright lines. If you want to understand more about that, have at it. But basically, Kirchhoff, whose picture we saw a few minutes ago, and when I say have at it, I don't say that casually. Again, you've heard me say it a couple times. I'll try and resist saying it again after this one time. You read what's interesting to you. And I think the fact that when you capture your own image, you are driven, you have an agenda, and that is, hey, I want to understand a little bit more about this thing I captured. There is an emotional attachment to things we create. That gives the impetus and some structure to otherwise the ocean of things we could be reading. So whether you get absorption or emission lines has to do with whether the light's going through a cool cloud, temperatures, pressures, things like that. Okay, so now how do we get, look, let's just say it this way. Suppose the Hubble Space Telescope people made a huge, huge mistake and they gave me time on the telescope. And I observed, I don't know if you can see that on your screens, there's a little dimming there in our beloved robin egg blue. And I tried to write a paper and submit it for publication. I saw a little dimming in that robin egg blue region. That's not science, right? So how do we get from qualitative, this beautiful rainbow spectrum, to quantitative? Well, what we do is we just plot this intensity. Let's take a look at it, and let's keep our eye on that little feature there. This peak here, that was a miscue. We'll come back to that feature in a second. That peak there is because the star is really bright. This is an intensity scale here. And over here, if we look closely, we can see that big dip from that barely discernible gap. Now we've got quantitative science. Now we can actually do some research. Now, and learning from the spectrum, we can compare it to other stars, other dates, other observations, all those things. That's how we learn what the stars are made of, how they're moving, and you'll see examples of that in the next few minutes. So how do we get that graph? So my story is, in 2009, I got a grating like this, and I went out in my backyard here in Seattle, 3 miles from Pike Place Market with my C8. I set it up. I was a terrible imager. So if you are, don't worry. You can do it too. You can do this just like I did. I think I was using, in fact, I'm sure I was using a Logitech webcam, and I had 2 star diagonals duct taped to each other because I needed some more back focus. I'm a software guy. I don't know anything about hardware. I break hardware. That's my job, it seems. It's certainly in the kitchen. I break a lot of dishes, it seems. I'm always in a hurry to get down here into my man cave. I think that's what the problem is. Or astronomer cave. Let's be a multi-genderal. So I came in that night at midnight. My blue jeans, the knees were grass stained because it was Vega I was looking at straight overhead. It was August. Next morning, I tried to create a plot like this and failed. I used some of the shareware which is out there. It was crashing. And to add insult to injury, the crashing error messages were in French. So, and I'll tell you, this is an honest confession. I gave up. I told my wife, this is supposed to be fun. This is a hobby. I'm just angry. I don't want to learn some new complicated piece of software that doesn't work well. So I put the grading in the drawer, but it just kept bugging me. I really wanted to do this. And so a couple of weeks later, I thought, I'll write a program that just does this graph. And by the way, this is that first spectrum I captured. So the next Sunday, I spent 3-4 hours. I created a graph like this. And now 15 or 20,000 hours later, I'm almost done with the software. So I hadn't intended to create it into a product. That's the software. R stands for real-time spectra, because you can do it with video, you can do it with images in real time. And this is just example of, I sort of missed a cue there. We'll come back in a moment. This is the Pleiades. You can see all the Pleiades stars have spectra. They're unique. Some have these double dips. Some have, these are peaks and dips and so forth. So this is the kind of thing you can do at star parties. I wouldn't do it at a dark sky site, but that's my software. This is actually in France. You can see Department de Physique. Anyway, I wanted to finish my story and just say that I know better than to give you a long software demo tonight. It's after dinner. If some of you have your microphones on, I'll start hearing your heads clunk as you fall asleep. But I want to spend 2 minutes showing you the software because I think it's important that you appreciate how easy it is to use. RSpec isn't PixInsight. You don't have to go to seminars at various conferences and watch, dozens of hours of videos. It doesn't pretend to be PixInsight either. It does one thing really well. And I've been developing software since the 1970s. And unlike the shareware people, in fact, that program that I threw under the bus a few minutes ago, I'm now friends with the author. I met her at a star party in France. And she said, I'm not a professional software developer. She's an engineer. She said, I tell people the software is free, the bugs are free. The software's gotten a lot better, but again, I wanted to roll my own and I really focus on making it easy to learn. So let's take a look. We'll come back to that in just a second. Here's the
just
software.
a quick interruption there, Tom.
Sure.
Would you like to take questions during the presentation or for people to save them to the end?
I think I'd like to wait to the end if that's okay. Is that okay with you?
It's fine with me. It was just one of the members put their hand up and then took it down.
Okay, great. Thank you, Gary. I appreciate it. So this is a FITS image, It could be color, it could be mono, it can be loaded automatically by the software every time it hits your laptop disk. And there's the star, there's the spectrum. You can see a little gap in the spectrum right there. If I don't cover it up, there's another one in robin egg blue and some others out here. So to capture a spectrum, the only thing you have to do is bracket it in like that. And then over here, we see that intensity graph. So again, as we saw earlier, that peak is because the star is bright, right? This axis here is intensity. And you can see there's all those gaps. You know, this little gap here I showed you is showing up there. So there's a step or two, literally a step or two between what I just did and getting this, because this axis is now calibrated. That's something for Q&A or another time, or the tutorial videos on my site, which walk through all this. What about those dips? What are they? You know, it's one thing to collect interesting data, but how do you make it interesting and how do you understand it? Most of the time as amateurs, especially when we're starting, which I still consider myself, there's people here doing far more advanced work. But by here, I mean in this meeting than I am. Most of the time we know what we're looking for. We've read about the star. This happens to be Vega. It's an A-type star. So we can come up here to a little internal reference library and see if what we're expecting to see is where all those dips are. So I'm going to come over here to Hydrogen Bomber and click the checkbox, and it's overlaid a template where the bomber lines would be. And you can see on the screen they're labeled. And those are the bomber lines going through our features. Are they exact? No. Does it matter? Not to me, because I'm not submitting research papers. If I want more accuracy and get that line right through that dip, sure, there are ways to do it. Do I need to do it? Only if I want to. So, and this, to be honest, this bugs me. The grading isn't exactly, now that I've dropped it, the grading isn't exactly linear, but this difference really, you know, I'm selling something. I want it to be, you know, right smack on. Let's look at how big that difference is. This is 4080 angstroms, and this is 4101 angstroms. So it's a 20 angstrom difference over 4,000. So that's less than 1%. That's like a 0.5% error, but it looks so big to me because it's my software. So that's all I want to show you in the software right now, or for the rest of my talk. I would ask you just to remember this view in your mind's eye with these bomber lines all showing, because we're going to come back to them and look at a scientific discovery which made use of those bomber lines. Okay, so we're going to come back to here. And let's see, get my show going again. There we go. So let's race through some examples real quickly here. Here's M57. There's the ring. When we look at the spectrum, in this case, there's only two wavelengths in this emission object. There's hydrogen alpha and there's some oxygen. So this is about the only extended object we can look at with a grating. It's bugging me that grating's on the floor, so forgive me while I bend down to pick it up. They are pretty much indestructible, though. I wouldn't do this if it was going to hurt it. I'm, you know, smearing my nose grease on it. God, that's the first time and the last time I'll do that. It's pretty gross. But again, you're just a Q-tip. It's just covered with plain glass, you know, astronomy, really good glass. But the actual grating that is delicate is buried inside. So there are just two objects here because there are only two emission lines. But we're, again, going to just keep going here. But if it turns out emission nebulas are your thing, then this is the kind of thing that, you know, you go, oh, now I see what I've been reading about. I can capture my own nebulas. There's other emission objects that I can capture. So if you want to look at something, oh, one other thing I wanted to mention, of course, this is a late stage star, right? So if you want to look at more detail on extended objects, then you need to dig deep. They're not cheap, these devices. There's some DIY ones for, you know, $500 to $1,000, but they're hard to use because they've got like a 10 or 20 micron slit that you've now got to find your target and stay on. Plus, these are typically just harder to use and harder to get started. And nobody really starts at this level. So, but if you have one of those slit devices, then you can look at a really diffuse object. This is M42, of course. It's the birthplace of stars. It's got the same hydrogen emission lines and oxygen. Now, I know at this point I'm thinking to myself, I'm sort of losing the audience. There's just lots of graphs showing, you know, relatively esoteric science compared to what we do most of the time. But stick with me. This is just a brief survey to give you a sense for what you can do. So this is pretty cool with just a 4.5-inch refractor and a video camera. We can see the methane, those deep absorption features on Uranus. Pretty amazing, huh? And what does that, we'll come back to that in a second. What is this about? Well, again, talking about curricula, suppose you want to work with students and do something about exoplanets and astrobiology, then talking about detecting gases on astronomical objects becomes significant. And if students capture this data, it means a lot more to them. And I was going to mention that for those of you who are imagers, remember that first image you captured? It was probably of the moon. That was for me. It was overexposed. It was blurry, but I could see a couple craters, and it was the most beautiful image. And I was like showing it to my coworkers and my spouse and my friends. And when it's your own data, you have that relationship to it. And that's what we want for students, as well as for ourselves as students at our age. Whatever age we're at, we always are students if we're lucky. So couple more examples. I wanted to just mention this. I know better than to try reading my bullets, so we'll race through it. But there it is. I forgot this was coming. I preempted myself. It's thrilling to capture your first spectra. And as you've heard me say repeatedly, you can do science with it. It's inexpensive. And I mentioned this earlier too. Your own data is very, very different than data that somebody else captured. And you don't want to go to dark sky sites. You don't have a PhD. And you don't have the patient skill or equipment or dark sky sight to do the kind of deep sky imaging. When I give these talks in person, I often at this point ask somebody in the audience to pull out a astronomy or sky and telescope magazine and just go to the back, that showcase where people feature their images, and find some beautiful, beautiful galactic image or nebula, and then show it, and then I ask them to read the fine print. And the fine print is like, this is 20 hours of imaging time. It's like, no, that's not me. I don't have that kind of patience. So, and I break things, as I mentioned earlier. I'll talk about that in just a moment. And we're going to talk about outreach in a moment also. So in 1881, Henry Draper, the Draper catalog guy, captured the spectrum of a comet. Back then, science was of interest to the general public, I suppose, maybe more than now for some. But we won't go there tonight. And so the New York Times published an article about it. Heck, if Hank can do it, so can we. So here is a comet. And again, you can see right down here that string of gems. Look at the bottom there. Look at that call out there. This is on an 80 millimeter refractor. Comets are extended objects, but they're often compact enough that you can do it without a slit. So over here, we can see the peaks from the swan bands. Now, I'd read about swan bands, but until I had this picture in hand done with my software, I really didn't remember or hadn't read much about them. This was captured by Vikant Agnihotri. He's in Rajasthan. Here's another example. Again, you can see the sodium lines, a little bit more recent of a comet. Now, this is one of my favorite slides. Anybody who uses, I'm trying to find my mouse cursor there. There it is. Anybody who uses a C-clamp as part of their telescope setup is my kind of observer. My problem is I'd probably crank it down too tight and I'd collapse the camera body. My favorite command on my Windows PC is Edit Undo or Control Z. It doesn't work in hardware. I mean, sometimes in life I wish I had a Control Z, but in this case, Robin is the designer of the Star Analyzer and he does everything well. There's the Star Analyzer. And he waited with a video camera to capture, and that's what this is right here, to capture the spectrum of a comet. That's the comet moving during one frame of his video. And there's the spectrum, and there was some sort of outburst right there. And there are some of the minerals he detected. Now, to be honest, I don't know much more about comets, except I like to show people this because it's sort of cool that it's something you can do. It's an esoteric aspect. We're not going to talk about the sun. We've all had plenty of sun over the last few years. But I do want to remind people if they've forgotten what the Doppler shift is, because I want to use it as an example or two. You know, when a train's going through the station with its whistle on, or a car has its horn as it drives past you and you're standing on the sidewalk, right? High pitched as it's coming towards you, low pitched as it's going away, right? Well, light does the same thing. So if we were expecting in a spectrum with a star analyzer or a higher end device to see this triplet, and instead of it being there, it was over to the right, we'd know that object was moving away from us, just like that train whistle or that car. If it was moved to the left, we'd know that it was moving towards us. There's an astonishing amount of science we can do with this. Now, this next slide will be the fastest exposition of what this particular type of supernova is. You've never heard one this fast, I can pretty much assure you. Two stars, they're just normal, plain old stars, binary stars orbiting one another. The more massive one gets bigger, and finally some of its gases get dragged into the smaller one and it explodes. End of the star's life. So here's one in M101 right there. I want to show you a video of, this is an animation of what it might look like as it went off. And you can see that explosive cloud going out from it like that. In fact, here's a photograph of a supernova, not this one. And you can actually see that shell, right? So let's see what we can do. David Strange in the UK used a 9-inch telescope. Now we're getting into stacked images, still star analyzer, less than 15 minutes of integration time. And he captured this spectrum. And that little bit of dimming, notice he's into mono now for more sensitivity. That little bit of dimming is that deep dip there. And that helps us identify it as a supernova. This doesn't look anything like the Vega dips or absorption lines look like. Now, this next slide won't be on the quiz at the end of my talk, but here we can see that this particular type of supernova has a deep dip right around 6,000, and that's silicon. That's how we tell it's a type 1A as compared to other types. You know, sometimes stars run out of fuel and collapse, that kind of different supernova. And this is the fingerprint for that type of supernova. Let's do a tiny little bit of fun. How fast is that shell coming towards us? This is the kind of thing that is used to win Nobel Prizes. Now, we won't be doing that winning, but this kind of tool, and I'll talk about that in a moment. So the observed wavelength of this dip is 6150. And if I got a bucket of beach sand and burnt it in the lab, if I had one, it would have been at that wavelength because it's not moving towards or away from me. Look, I couldn't remember the Doppler shift formula, but there's not much math here. Even a knuckle dragger like me can do this. So I plugged all the numbers in. We've now measured the speed, the blue shift of that supernova shell coming towards us. There should be two wows there. One is, wow, that's fast. The other is, wow, I cannot believe I did that on a backyard telescope. Now, these types of supernovae were used by Adam Rees. His team won the Nobel Prize, he and his team, for studying using supernovae as standard candles, the accelerating expansion of the universe. This is a little bit in contention now, but again, great observations. And like usual, typically what we're doing as amateurs is following in their footsteps, standing on their shoulders, whatever analogy you want to use, to actually do some of the things they've done. And so it becomes memorable. What about the spectrum of a black hole? Just checking out the time here. We got a little time. So a black hole doesn't have any light emitting from it, but the circumstellar disk, the accretion disk, I don't know if we'd call a black hole stellar, so I'll take that part of it back. But the accretion disk is very hot as it spirals in, and that does emit light. So David Hayworth, south of me in Oregon, in Portland, captured this spectrum, and you experienced observers know exactly you can just spot 3C273 in that, right? Well, Fortunately, I didn't know either, but he did. It's there, and those two arrows are pointing to two bright spots. There are those two bright spots. There's the spectrum. Okay, so this guy, Martin Schmidt. Now, when I'm in person in an audience or I have a view of an audience, I'm always looking for somebody who's relatively young so I can talk about age and mention them. He was in his 20s when he got this spectra. He captured, or he was provided this spectrum by professionals. He was a professional too. I think he was at Princeton at the time. And like any scientist, he has an unknown, and he goes, let's compare this to a known. So this is the image from my software I asked you to keep in your mind's eye. And so he said, well, here are the Balmer lines. Do any of these Balmer lines line up with features that I'm seeing in this spectrum? And he went, not really. That's a poorly drawn line. Not really. So he reached the conclusion, well, those aren't Balmer lines, those peaks. I don't know what they are, but they're not hydrogen. But they were. They were shifted to the side by the cosmological expansion. And you can do this with a small telescope. There's a beautiful transcript of his on our site, and you can either find it there or contact me off the site, and I'll point you to it, where he talks, it's an interview of his, and he talks about making this discovery. It was such a simple solution. He was worried. It's great. It's great to know that these great scientists have the same imposter's complex that all of us have. I certainly do. And he said, what if I'm wrong? He had colleagues come in, what if I publish and, it turns out I've made a rookie mistake and my reputation is ruined. And then he went home that night to his wife and he had some wine. And she was sort of surprised because he never really drank wine during the week. She said, what's going on? He said, something terrible happened at work today. She said, what? He said, I made this discovery and I'm afraid that I may be so well known, I'm not going to be able to do my work because people are going to be demanding my time as a celebrity. Now, Kim Kardashian would have been happy to be in those shoes, but not so much Martin Schmidt. So what was the discovery? Well, first of all, we're able to make the same discovery here. But the discovery was that this object over 2 billion light years away was still visible to us, which meant intrinsically it was incredibly bright and yet that far away. And so what's amazing to me is light that has come such a distance, and I put that in air quotes, or over so much time, because who knows what time and distance means to a photon. So I don't. I read about relatively every few years and go, oh, that makes sense. And then the next week I've forgotten it. But light has that information that we can tease out of it. It doesn't seem to age if it experiences time. Unfortunately, we humans don't age as well. This is Martin Schmidt a few years ago. He's since passed away. Friends over the years have accused me of throwing him under the bus with this picture, but really, I'm just jealous of his full head of hair. He's a lucky guy. That's all I can say about that. So now let's talk about the tease that I shared with you a little earlier, and that was doing outreach. As you heard a month ago, and I mentioned, Pat had trouble getting into high schools. I want to show you some projects that high school kids do, of the types of projects that Boyce Astro will be doing and Chandra will be conducting classes on. And we'll talk about that a little bit more in a minute. This is a young woman who observed the same thing. Oh, this was, what was this? Now I got to lean around my camera. I've got this stupid camera between me and my screen so you feel like I'm talking to you, right? But sometimes it gets in the way. So, okay, this is a galaxy. Well, you can do this with galaxies too, and I've got examples of that on the site. Pretty cool project, huh? I want to show you another project. Now, these are projects where these young people have a mentor. So, and these are the projects that go to STEM fairs and win. So this is a funny slide. It's the first time I've shown this slide. I don't want to show you too much text, but I will show you a little more. This is an email I got last September from a young woman named Nicole. I'm really interested in going into stellar spectroscopy, excited. I have DSLR cameras, but I don't have any money. Could I buy a grating on Amazon? Unfortunately, it's tough to do. I mean, this kind of diffraction grating has some properties that make it excellent for capturing images. But, what mentor or potential mentor or teacher doesn't like? I mean, this is the cream of the crop kind of student, right? And here she is in June. She won her high school science fair. She won her regional Utah Science Fair, and she was accepted in the National ISEF Science Fair. Now, this is not as high an end a project as many of the science fairs that we see in other disciplines. I look at some of these science fair projects in bioinformatics, and it's like, oh my God. But I think I can zoom in on this. Let's see. No, I can't. I had another copy of it somewhere. Um, so you can see there's a star analyzer, there's some diffraction glasses, there's talks about different types of stars, future works, there's the HR diagram. So what we did here is we gave her a star analyzer because giving back is something we do, and I imagine you all would like to do also. And I got online and found an astro imager. He was the president of the Ogden, Utah Astronomy Club. And I got him together with her, and her father accompanied them on all the meetings. This picture is used with permission of her father, who captured it. Theirs is, I think it was a C8. You all would know better than me. ZWO camera, grading, and so forth. So you can mentor these kinds of projects. It doesn't scale well because it's, each one teach one kind of thing. What we're trying to do with Boyce Astro is change the dynamics a little bit where we're now capturing spectra like the ones I showed you tonight. And that will allow students to work on spectra that they feel some sense of ownership to. I would prefer to have them out adjusting a telescope or even remotely adjusting the telescope focus via, a zoom capture to the telescope control software. That doesn't scale very well. So, but this is the kind of thing. I'm working on an article for Sky and Telescope magazine now. I don't know if they'll accept it. I was a contributing editor for about 10 years, no longer, where I would like to see a cadre of amateurs like some of you and myself and Chandru and Pat find a way to work with students and bring this to them. And, I want to drop some buzzwords here for a minute. We'll get to those in a second. I want to show you another example. This is what you could do. This is my software and a gas tube. And there is our robin egg blue for hydrogen. And this hydrogen image shows up as a peak over here. You can see those lines. Now, what a student captures this with is something like this. This is our little RSpec Explorer. You can see, let's go back here, there. And you could, now this is, again, I don't think a lot of you are going to take me up on this, but you could, look, you don't have to learn a lot of spectroscopy or the science to do this. You can reach out to a chemistry teacher in a high school. We have lots of high school teachers using this equipment. And you could say, I'd like to come in. I'll give you all my slides to help. Come in. I want to. Now, why chemistry teacher? Because they have to teach this. Physics teachers, they can skip it, but they often don't. Earth sciences teachers, why would they want you in? And this is the buzzword I needed to look up. I wasn't sure of the name. It's called cross-cutting concepts in state-of-the-art NGSS science. And it means interdisciplinary. And so you would come in, they all have these gas tubes in their classrooms, or you'd have your own gas tube you'd bring in. You'd set this up. Okay, it's peaks, big deal. But then this is really amazing. When you click here, this is called the energy diagram for hydrogen. The software lights up that peak. So now you're reinforcing what the educator wants the students to learn. Advanced students can calculate this energy level and then determine, let's see where my mouse is, determine this wavelength. I don't want to get too carried away with this, but here is the keystone, this next slide. Then you invite them out to look through your telescope and capture the data. And this is what they get. They get two graphs. The red graph is from the classroom. Those are emission peaks. The blue graph is Vega. And notice Vega has these absorptions. The gas tube has the emissions, but they line up. The students have now just discovered hydrogen on Vega with their own hands. The principal, the educators, not only the chemistry and the physics and astronomy, but math professors, and that's the kind of thing Chandra is putting into his course, not only capturing the data, but then processing it, writing some of the Python code to process it, understanding how this kind of data ties into the HR diagram and life cycle of stars. Okay, two more quick examples. I've got just a couple more minutes. I'm going a little long here. That segment is a new one for me. So far, we've been looking at, okay, wake up, guys, I'm gals, I'm almost done. There's my mouse. So far, we've been looking at just this hydrogen alpha feature, for example, how wide it is. It's about 50 angstroms. Suppose you want to zoom in on that. That's when you really need to go to a slit spectrometer, those expensive ones. This is that same absorption line as that one, but again, with much more resolution. This is Vega. We can compare it to the moon that's not moving towards or away. And now we've calculated the radial velocity of Vega. You can't do that with a star analyzer. You need a slit. Final example of the night. So, and I have a visual aid, and I'm going to stop my screen sharing for a second so you can all see me. This is a spinning star. Use your imagination. This edge is moving away from you, so that light is red shifted. This edge is moving towards you, so it's blue shifted. Normally, stars spin slowly, so that doesn't have much effect. But if it's spinning very quickly, it does have an effect. Let's look at what that effect is by coming back to the slide and looking at a star. Oh, first of all, there's a diagram of what I just showed you. This edge is coming towards you. This edge is going away. Let's look at a star that is spinning very fast. Notice how the data is smeared out. Some of it got stretched into the blue. Some of it got stretched into the red. Pretty amazing that we can do this.
Tom,
Yes.
we didn't see that. We didn't see that.
Oh, thank you. Yeah, I sometimes screw that kind of thing up, and I appreciate your reminding me. I was so proud that I got back to my PowerPoint show quickly. I forgot to start sharing my screen again. So thanks so much. We're in the home stretch. Let's go back to that one slide, and that's this slide here. There's Vega. There's the diagram with the blue coming towards you and the red going away from you. And when you look at a star spinning quickly, you see a very broad peak. It's amazing, the ingenuity of humanity and scientists to look at a rainbow, basically, and be able to figure out how some distant object is spinning, how fast it's spinning, or what it's made of. Okay, how do you get started really quickly? I've mentioned the star analyzer a handful of times, almost any camera, almost any software. This is the software, which I'm always a little embarrassed. I get a little emotional talking about it because it was so frustrating on and on, early on for me. Both of these are written by, this by a woman in France, this by a guy in France. Brilliant. He is brilliant. The two of them pioneered this whole field in the amateur world with several others. Both of those softwares have gotten better. This one is really the gold standard, but harder than PixInsight to learn. And you might need some sort of spacer in here, and I can help you with that. There's tons of books on the topic. They're all on my site. Some of these I have in PDF format. They were originally published for free. Let me know if you would like to take a look at that PDF file from 12 years ago. Our site has a lot of information on it. About 10 years ago, I taught a workshop to about 100 AAVSO members at the SAS conference up in LA. And we recorded that workshop, and it's now available on my site. And the software is free for 30 days. So tomorrow you could sit down with the video on YouTube and my free software for 30 days, and you could walk through and actually do some of this yourself. The AVSO now has a database that you can contribute spectra to for professionals to access. There are opportunities for pro-am collaboration. Not as many as we'd like, but there are some, and more coming, I think, in time. So we've come a long way in the last 50 or so minutes, as well as in the last several hundred years. I'd like to thank you all. Occasionally I got smiles out of those of you I could see, and but thank you all for inviting me tonight. Those of you doing outreach, more power to you. and I'll be here to answer questions until they sort of drag me off the stage and I find myself booted out of the meeting. Thanks again, everybody.
Tom, that was amazing. Thank you so much. I mean, 50 minutes just flew by. We hope you come back before another 11 years passes. But at this time, let's just take our time for those who want to hang on. If you have questions for Tom, please either unmute or put something in the chat. I'll be monitoring.
Okay, this is Chandru. Tom, I just wanted to say thank you so much for that lovely presentation. And I wanted to let everybody know that we're going to be teaching a class called Barospection. It's going to be free for anyone to attend. It is using Tom's software and the Barrow telescope from Boyce Astro. So not only now you will not need any of the equipment that Tom talked about, but you can actually image through Barrow, which is part of this class that we're going to offer in August. It starts in August, and so please go to this website here, and you can register for this class. And I just wanted to say on the outreach subject, Tom, I took your grading and we put it on an 8-inch telescope at my high school that I used to teach at. And it was amazing. So we did all of those things that you talked about. But also, spectroscopy leads to really an interesting way to learn mathematics. And so I also taught geometry. So a lot of my mathematics students attended my astronomy sessions. But I just wanted to say, for the first time, physics students and mathematics students were able to measure something as small as an angstrom, or something as small as 10 angstroms. Let's say that is 5 nanometers in length. There is no way any physics lab you go to, you cannot measure something that small to that accuracy. We can do it through the SDAA 100 grading, which is amazing. So, and then the mathematics associated with spectroscopy is all high school mathematics. You don't need to know freaking, fast Fourier transforms or, any fancy stuff that you need for subjects like speckle. It is very accessible. So spectroscopy is something that high school students can get very excited about. It is very interdisciplinary. And I can speak from experience doing that. And so I'm now very honored and fortunate to be teaching the Intro to Spectroscopy class under Boyce Astro. So open invitation for any of you to attend. Tom and I set up, with Tom's help mostly, set up a SDAA 200 grading on the CDK 17, which is in your facility at the San Diego observing site. And so there is a telescope dedicated for that. And we'll be using that to obtain spectra live and process the spectra during the class. So that's it from me. Thank you, Tom. Amazing presentation.
Thanks, Chandra.
Tom, I have a few slides using the SDAA 200 that kind of would dovetail quite nicely into the back end of your presentation if you're interested.
Oh, great. Sure.
Okay, can I share, B?
Yeah, sharing's enabled.
Okay, so I'm going to share. Okay, hopefully you can see this. I'll run through it pretty quickly. So for those of you that don't know, I coordinate a group called the Red Dwarf Group. We are a group of about 40 astronomers, mainly in the US and Europe, that observe flare stars. And this, the slides I'm going to show you were presented on March the 18th to one of our Red Dwarf Group regular meetings. Sorry, are you seeing the video? Okay. Okay, great. So this is my observatory sitting down in the bottom there. It's a fully autonomous observatory based around a C8 and Williams Optics 51 millimeter refractor. So I'm just going to then step forward. Okay, so one of the flare stars we were looking at the beginning of the year was AD Leo. I was doing photometry with the 51 millimeter Williams Optics refractor. The C8 with a 0.63 focal reducer in SA200 was used to do the spectroscopy side of things. Both of these systems were running simultaneously at a imaging cadence or an imaging cadence and length of 30 seconds. On the 26th of February 2025, I observed a flare in the V band, a flux increase of about 40%. That's put that in magnitude terms, that's about 0.36 of a mag increase in the brightness of the star in V band. Not a particularly large flare in terms of flare stars. Sometimes you can see flares increase by as much as can make the visual magnitude of the star increase by as much as 2 magnitudes. So, but still a significant flare. This flare was fairly unusual in so much as it decayed extremely quickly, and I was using AIJ for the photometry and RSpec to do the data processing. And basically, this was a 6-hour run in which this data was collected. So here is the flare. So this shows you the flare in V band. You can see the 40% increase in relative normalized flux. Really fast rise time. You're looking at about a minute, and the decay is taking place over a period of about 10 minutes there. That's actually quite a quick decay for a flare. We typically see these are a bit longer. The target is shown in blue, and the check star is shown, or actually the comparative stars in these cases are shown in the pink and well, both pink colors. Basically, you can see those are flat. So here is the raw quiescent spectra of the star AD Leo captured using, so I was using a 533 MC camera on the C8 30-second exposure. And here is the raw spectra. To Tom's earlier thing, you can see the 0 order, which is the star itself. This spectra has been wavelength calibrated, so you can see that I'm getting spectra over about 400 to say close to 900 nanometers, or 4,000 to 9,000 angstroms. So one of the first things we need to do if we take a raw spectra of this type, and I'll just define quiescence. So quiescence in the case of a flare star is its state when it's not in the flaring event. So this is how you would just see the star regularly. So one of the first things we need to do is we need to do an instrument calibration. That means to say we need to calibrate for the QE response of the camera. That tends to be a little complicated with the color camera. As you can see, it's got a couple of bumps in it. But once we do the calibration, we can then produce a calibrated spectra. And this is the calibrated spectra. The spectra is in red. Now I've got to remember which way around this is. So what I've done here is I've taken the quiescent spectra and I've then gone out to the Pickles library, which for those people who get into spectroscopy will become one of your best friends, that basically shows you the spectra you're expecting from the star. So if you can see the comparison of the two spectra there, they're pretty close. So we know that we're getting good data. So I then take a couple of 30-second exposures from across this 6-hour thing, and I kind of compare them in the quiescent state. And you can see that they compare really well, right? If we take a spectra at the beginning, so frame 17, then frame 46, and then frame 100, and then frame 200, 30 seconds apart, all these spectra are pretty much on top of each other. So we know that the system's stable and we're able to do this measurement in the quiescent state. But what happens in the case of when we see the flare? So here is the results for frames 30, 31, 32, 33, 34, and 35. And what you will actually see here is, and there's an animation that I'll put up briefly at the end here, which kind of makes it a bit more obvious. But you can clearly see that as we are run through the flare event itself, we see a significant increase in the blue end of the spectrum associated with the spectra of this star. So what's happening is the flare event's taking place. Flares are typically hot events, and so it's making the star look hotter, and that corresponds to an increase in the blue end of the spectrum flux that we see when we're looking at the spectra. This is looking at it in a little more detail. Again, we can see that that flux has increased quite dramatically for the blue and the green, which are associated with the peak of the flare. And hopefully, if this plays, you will now see an animation of that event taking place. So this is a looping animation. So we're at quiescent about now. We then go in.
Can you point out the discrepancy that we're seeing in the feature of 4850, just so people know where you're talking?
Sorry, I'm not sure I understood the question, Tom.
Can you point out the differences? What were the two curves that are outstanding because it's not quiescent? Yeah, yes. Right there.
Right here. So these are the two frames associated with the peak of the flare. And so what we're seeing here is a fairly... And to be honest, this isn't a particularly large flare, but we're seeing a significant increase in flux at the blue end of the spectrum. So that was really what I wanted to show you. So the red dwarf group, as I said, has a few SDAA members in it. Predominantly a lot of other folks as well. We use low resolution spectroscopy, and we also do some high resolution spectroscopy. But this is kind of nice because it does show you what's happening sort of, you know, at a coarser resolution, but across the entire spectrum of what's going on within when the star is in a flare state. Okay.
That's beautiful. That's really beautiful. It's nice high-end science with simple equipment. What did you say the size of your telescope was? It was less than 4 inches, right? It was an 80 or something?
No, so I'm using the SA200 is on the optical train, consists of a 0.63 focal reducer, which is on a Schmidt-Cassegrain 8-inch telescope.
Oh, okay.
And then for AD I was using the Williams Optics 51 to do the photometry.
That was it. Thanks for that presentation. That's great. It's good to see you using it this way, Gary.
Yeah, and you know, we've already put a couple of publications out now, both on the well, the group itself has now, I think, done 7 or 8 publications, mainly the JABSO, so Journal of the American Association of Variable Star Observers, SAS, and a couple of more high-end, more scientific stuff. So our goal is to basically try and put out a couple of scientific papers each year.
Beautiful.
Okay.
Thanks.
Thanks, Gary.
Any questions?
Any other questions for Tom?
While people are pulling up their questions, I have 2 quick things to show. This is one. This is Albireo in mono. Now, can you see that? Can you see this screen where my mouse is?
Yes.
Okay. This is Albireo A and B. And right now we're looking at the cool one. Notice the shape of that curve. There's more energy out here in the blue because this is the hotter of the two stars. This is actually a video done at the telescope live. In a moment, you'll see these sampling lines going up to the other of the two stars, and watch the shape of the line change because now this is the cooler of the two stars with more energy in the red. So this is the kind of thing, this is just the beginning for the kinds of things that you just saw him do. This is, fundamental science that helps people understand what's going on. The other thing, again, I don't do a lot of anything, to be honest, here in Seattle with all the rain. But this sample I showed you in RSpec, and this will be 20 seconds and then we'll be done, this is Vega, literally that first night out for me. I'm going to play this video. Now, remember, a video, it's less than a second per frame, and we're getting interesting data. If we zoom in on the star, we can see my seeing here in Seattle was terrible. And we can see the spectrum is jumping around here. But we can also see that it gets steady when I turn on stacking. But if you're doing star parties and you have this sitting here, and as Chandru mentioned, he did some of this at his high school here in Seattle. And when you have a bunch of students and parents out looking at telescopes at a star party, in the city or at a dark sky site, and you have this screen that you're seeing here showing, it's colorful, it's moving, and it's the springboard, which gives you an opportunity to talk more in depth about what people are seeing. So I wanted to show those two just because I thought they were exciting in terms of what can be done, whether it's the fancy stuff and the more advanced stuff like Gary just did, which isn't all that hard, or the more simple observations like this. You can grow over time into doing the more advanced work. Thanks.
So I think I'll add to that, Tom, and say I am not a spectroscopist at all. My interest is photometry. Dave, who's also on this call, kind of got me interested in the spectroscopy side. He runs an Alpha 600. So I bought one of your little SA200. It just goes straight in the filter wheel of my system, right? So I can just swing it in any time. I think with Dave's help, it took me 3 evenings to master the software and capture that data. It's a really simple system to use. It gives you a broad picture of what's going on and what you're seeing. It's tremendous fun. And as you rightly said, Tom, I've done real-time photometry on a fast eclipsing binary at a star party, and the public just ate it up. I mean, they just found it incredibly good. And I think if you are doing this type of thing, where you're showing the spectroscopy of a given star and how that changes from one star to another, which is, easy to do as slewing across from one place to another, obviously. This is just a incredibly good tool, and I must say I appreciate the effort that you put into putting all this together. And RSpec is a very useful and easy to use tool.
Thanks, Gary. Clearly you drank the Kool-Aid, and so did Dave. Thanks so much.
Oh, yeah, that's true.
I have a comment. For those of you that might remember, Steve Shore presented to our club more than a year ago. Some of us know who Steve Shore is. He's the head of the spectroscopy division for AVSO. He lives in Italy. He's just a fantastic resource. What Steve said in his meeting more than a year ago was that stars are living things. And this is a mantra that I've been taking to star parties for a long time, but he brought it right down to the point where, stars are born, stars have a life, stars die. They have personality, they have individuality. They interact with each other. They build structures in the universe. They're basically living things. And as we study these things, we begin to realize that all those points of light out there, every single one of them are as different from each other as we are people on Earth. It's just amazing when you get into the personality, the characteristics of particular features out there of different kinds of stars. This project, the Red Dwarf Group, is fantastic. We're looking at changes in the photometric data, doing B minus V calculations. And with a spectroscope, you can see the changes in the ratio of the intensities of the H-Balmer line series. We call that the Balmer decrement. You can see it actually change, and it changes at a funny time scale that is not linear. So if you do time series spectroscopy, you can actually see those lines change and how they change the color of the emission of light from that, from that star. So to me, being able to actually visually see and record data that shows that these stars are so completely different and so full of energy and so full of individuality and personality that it's very intriguing to chase those things down. You just can't stop doing it. So anyway, thank you, Tom. You've been a great mentor to me starting about 4 or 5 years ago, and I really appreciate. I'm still using your software, by the way, with an Alpi 600, and I could go to ISIS. There would be some benefits in some of the features, but the user interface is so difficult, and I can do everything I want to do right now. So it's been a great tool for me. Thanks again.
Thanks. Thank you.
And
Raised by Stefan.
Yeah, let Stefan go.
Go ahead, Stefan. You're muted.
Try to. First of all, I'd like to thank Tom for this wonderful presentation, and I thank from India, southern part of India, and I have been teaching spectroscopy for 30 years at the master's level, but now I can understand how this can be brought in for astronomy outreach. And I'm also happy to share that I'll be coordinating with the Boys Astro for the upcoming spectroscopy program. So we'll have more interaction. Thank you again for this very nice presentation. Thank you.
You're welcome.
And I'll just add one comment to follow on from what Dave said. So he kind of mentioned timescales with respect to this, and just going back to this flare stuff, this kind of hit home the other evening, and again, it's nicely demonstrated by the data that you can collect either from a photometric point of view or from a spectroscopy point of view. AD Leo is about, if I remember correctly, I think 16 light years away, right? So it obviously takes 16 years for that light to reach a telescope here on Earth. That star is probably going to last hundreds of millions to billions to a billion years in terms of length, which, is a fairly large number in the sort of age of the universe, right? Which is around 13.6 billion years. And yet we're able to see events here with simple equipment, both spectroscopy and photometry, that are taking place in 2 to 3 minutes. I mean, just think of the enormous magnitude change of what you're actually seeing there, right? Events that are taking place on a star that's 16 light years away that will be around for at least 100 million years, possibly a billion, and yet we're able to do really significant measurements on it of events that are taking place in seconds to minutes. And all with a small little device that's this big that just drops into a filter oil. So again, great presentation, Tom.
My mistake, sorry. This is our Lyrae in just 2 hours of imaging. It's an animation that my software, it's captured on my software, but not animated in it. 4-inch refractor. And with this star, you can see the shape of the curve as well as the Balmer features coming into view. Look how deep they are there. And then it drops down again. So this is the kind of thing that you've been hearing about tonight. I thought I'd show you this animation. It's so lively. And I love what you said about earlier about Steve Shore talking about stars as being living things. He's really drunk the Kool-Aid, and it's wonderful to hear him. It's poetic and I think a deep way of looking at things to enliven the universe in the way that he describes.
Any more questions for Tom?
Thank
All
you
right. Looks like this one is a wrap. Tom, can't thank you enough. Gary as well. Thank you so much, you guys. A really great program.
Hey, my pleasure. And yeah, Tom, fantastic job. Really appreciate you coming on and talking to the group tonight. And hopefully a few more of our members will catch this on the YouTube posting.
You bet, Gary. You're welcome. Thank you for doing such great stuff with the tool. And you and Dave knew most of everything I was saying, so you had to sit through a little bit more worse signal to noise ratio than some of the others, perhaps. So thanks for sticking with me.
You know, it doesn't matter how many times you listen to this, right? You learn something every time. So it's always useful stuff.
Sure.
Awesome. Thanks again, everybody.